There is one very important additional fact you need to know about viscosity, and that is that the fluid immediately adjacent to a solid surface cannot slip relative to the surface. What is more, the particular material of the surface, wood, metal, glass, plastic, cannot in any way alter the viscous behavior of the fluid. This liquid is glycerin. I am loading the marking pen with colored glycerin. The fluid immediately adjacent to the surface of the cylinder moves with the surface. It does not slip. Because of viscosity, the fluid farther from the cylinder also moves, but at lesser speeds as the distance from the cylinder increases. Let's see what this change of speed with distance does to a fluid particle which is initially square. It causes a shearing deformation. But because of viscosity, each fluid particle resists being deformed. And so we have to apply a torque to overcome all this resistance. Here is an instrument, a viscometer based on this principle. An electric motor rotates a cylinder in the fluid at a known speed. The torque required to rotate the cylinder is measured by a spring and is read on this scale. From the speed and the torque and the dimensions, we can work out the shear stress and the rate of shear deformation, and in that way get the viscosity. Here is another interesting fact. The frictional resistance between a solid and a solid depends on the normal pressure of contact. But in a fluid, the frictional resistance is almost totally independent of the pressure. It depends almost solely on the rate of change of shape of the fluid particles. Now we are ready to come back and think about how all the forces we have been discussing affect the motion of the fluid. First of all, it turns out that we need not consider gravity at all. In our experiments, the terminal speed experiments, the wind tunnel experiments, gravity in the fluid produced a buoyancy force which decreased the apparent weight of the objects. But we measured only the net weights, and so the circumstances of our experiments were such that gravity was automatically compensated for. And the other body forces, electrical, magnetic, were not present in our experiments. This leaves us only with the surface forces, that is, pressure forces and viscous forces. Now, the way in which these two forces control the motion of a fluid particle is governed by Newton's law of motion. If we add vectorially the net pressure force with the net viscous force, we get a resultant force through the parallelogram construction. This resultant force is equal to the product of the particle mass with its acceleration, or for a particle of unit mass, it is equal to the acceleration itself. Now, this instantaneous acceleration controls the motion on the next little bit of particle trajectory, and so on for successive bits of the trajectory. Incidentally, the instantaneous direction of the particle motion need not coincide with the direction of the acceleration vector, nor for that matter need it coincide with the direction of either of the two force vectors. Here is a sketch showing the parallelogram of forces, and here is Newton's equation. Net pressure force plus net viscous force equals the product of mass with acceleration. For short, this mass acceleration product is often called the inertial force. We need not concern ourselves with the mathematics of fluid flow, because we can understand a great deal merely by grasping the notion of this balance among the three quantities: pressure forces, viscous forces, and inertial forces. The explanation of many diverse and puzzling fluid flow phenomena hinges crucially on the realization that in different experimental situations, these three quantities are of different relative importance. For example, suppose that we had a fluid of very small viscosity. Then the viscous forces would be very small compared with the inertial forces. For many practical purposes, then, we might entirely neglect the viscous forces, thus leaving us with a simple balance between the net pressure force and the inertial force. Here is Newton's equation for fluids of very small viscosity, with the viscous forces neglected altogether. We have the balance between the pressure force and the inertial force. And in the vector diagram, the vectors for these two forces must coincide. This is for the case of fluids of very small viscosity. Now let's look at the other limit, fluids of very large viscosity. Now, the viscous forces are so large that they overwhelm the inertial forces. And for practical purposes, the inertial forces may now be neglected, leaving a balance between the pressure force and the viscous force. In the vector diagram, the vectors for these two forces must now be equal and opposite. By thinking about these two extreme cases, we realize that the type of flow may be categorized in terms of the relative importance of the viscous force and the inertial force. Viscous force, inertial force. Viscous force, inertial force. Perhaps in terms of the ratio of the two. Let's look into this. Here are several objects of different size, but they are all of the same shape, and so we say that they are geometrically similar. Scale models of airplanes and ships are geometrically similar to the full-scale craft. Imagine that we carry out a series of drag experiments on objects of this specific shape. In each experiment, the particular object used may be identified by a single dimension representing its size, say its length. In each experiment, we might have a different speed of the flow. And in the different experiments, we might use different fluids. For example, air, water, oil, and so on. We have seen that the important mechanical properties of the fluids are the density and the viscosity. Here are the values of these two properties for air and water at the temperature in this laboratory. In the different experiments, the magnitudes of length and speed may vary over an enormous range, just as the density and the viscosity do. All the experiments of the series would appear to be very different from each other, and in general they are unrelated. But consider a special situation. Suppose that in two of the experiments the several quantities in Newton's force balance bear the same ratio to each other. Then those experiments are dynamically similar. And from the point of view of mechanics, they are in a sense identical experiments. Now, different experiments are dynamically similar only if a special combination of these quantities is the same. That combination is the density times the speed times the length, all divided by the viscosity. This ratio is called the Reynolds number, after the engineer-scientist Osborne Reynolds, who gave us the first clue to this idea about 80 years ago.